Cool. So we're going to start looking at some of the applications of differentiation in this class now. Up until now, we've looked at how to basically do differentiation for different kinds of functions under different kinds of scenarios, whether you might use like your product rule, quotient rule, chain rule, that sort of thing. Now we're going to start looking at what you can actually use differentiation for. Now, fundamentally, differentiation is all about trying to get information about gradients or rates of change of a particular function. And one of the applications of that is finding what are referred to as the tangent lines of a given function. You would have actually already seen questions related to this already in the chapter, which is a bit strange because it doesn't show up like as its own section until chapter 10, but all throughout chapter 9 those questions do ask you stuff to the effect of what is the gradient of the tangent. The tangent is a linear line that connects to the function at a particular point. So it doesn't exist in isolation, it always exists with respect to another function. Not only does it intersect a function at a particular point, it also shares the gradient the function does at that point as well. So those are the two key features of the tangent line. Because I mentioned that they have to share the same gradient, this is where differentiation becomes applicable. You would use differentiation to figure out the gradient at that spot on the original function, and therefore the gradient of the tangent line must share that same gradient. That's pretty much it. You're still finding a linear, so fundamentally you need to know the gradient and the y-intercept of your linear, or in other words, just gradient and a point, effectively. If you can find the gradient and the point, you'll be able to solve that linear either by using the gradient point formula that I have highlighted here, or if you do the y equals mx plus c approach, where you just sub in the point and rearrange. It's fundamentally the exact same thing though. As for how you find the gradient of that tangent line, by far, like 9 times out of 10, you're going to be doing this, which is what I mentioned before, finding derivative of the original, and therefore getting the gradient of the original, which transfers over to the tangent line. There are a couple of other use cases though. Sometimes just doing derivative won't necessarily get you exactly what you needed. You might get it in terms of coefficients rather than in terms of actual values themselves. So in order to then eventually solve for those coefficients, you need another method that is equivalent. One of which is to simply do your rise over run. As long as you know 2 points that the tangent line has to pass through, it is still a linear, fundamentally. So you can do a rise over run approach to get another way for finding that gradient. The other approach could be if you have angle-related information. From there, you could just do tan theta. So let's say you had an angle of 45 degrees as part of your known information. You could just do tan of 45 degrees, which will give you gradient 1, and that'll be another way of getting gradient-related information. So the simpler questions are going to be just do diff, and then that'll be it pretty much to get your gradient. Some of the more challenging questions will be do diff, and then another one of these to create your second equation to solve any further unknowns. Is it fair enough why tan theta gets you gradient, by the way? Do I need to refresh that?
No, makes sense.
Makes sense? Cool. Awesome. Okay, so here's a really basic example, just straightforward, finding the tangent line using differentiation. Here's all the steps at a higher level. Let's see how they look in an example. So basic function x squared, and we want to find the tangent at x equals 2. This is usually not much of a step, more so just collecting information. You might need to solve for the full point. Like in this case, we know f of x clearly, and we actually only know the x value that we want to find the tangent at. For gradient point formula, or actually getting the full linear, we need the y value as well. So real simple, chuck x into f of x, and you're going to get the corresponding y value. We've done this to death in many other cases. Next up, finding the derivative. This is going to lead us to getting our gradient. So x squared now goes to 2x. From there, because we know the point, or more specifically the x value at which we want to find the tangent, that's the x value we're going to use in the derivative function. So f dash of 2 is going to get us the gradient at that spot, which is also going to come out to 4 in this case. We have our gradient, we have our point. I've always preferred to just use the gradient point formula and then rearrange it. You can do a y equals mx plus c approach, and that's perfectly fine as well. In fact, I think I literally counted the lines of working between both, and they come out identical anyway, whether you do y equals mx plus c or whether you do this. They end up coming out to be identically the same amount of lines are working, so you'll save no time either way. That's the most straightforward of the examples that we'll have a look at, so worth pausing here for a bit to see. Is that all good, fair enough?
Yep, that makes sense.
Easy. All right, let's step it up then. So these are the kinds of examples where you now have to start doing a bit more than just f dash. So in this case, what we have is a point, yes, but the point is generic. It's just some x value where x equals a, and the y value, well, by extension, will just be essentially replacing x with a. All right, so you just have what is effectively a generic point on your function. We're also told the tangent passes through the origin at whatever that generic point is. And rather than our goal being to find the tangent line, we have to figure out what the value of a is going to be. So basically, we need to figure out how to get equations that have a in them. And because we're working with tangent-related information, doing differentiation or other gradient-related things is going to be helpful here. So first up, because we know 2 points that it goes through, the origin as well as this generic point, we can get the gradient via the rise over run equation. y2 take y1 on x2 take x1. Simplify things down, and you've now got one way of calculating gradient. You've got this expression, m is equal to that. But those are 2 variables, right? You've got the m and the a. E doesn't count, that's a special number. And because we have 2 variables, we are going to need at least another equation to solve one or both of those variables, get them to an actual known value. That's where our diff is going to come into play. So because we also know f of x, whenever you have f of x, you can always get f dash. So f dash in this case, do a little bit of a chain rule, basically taking that coefficient of 3 down the front. Now, we are also trying to find the gradient at this particular point. So instead of just using the generic x in f dash of x, we're going to replace it with a, which obviously doesn't really do much, but it makes your working out a lot clearer as to what you're actually doing. So effectively, this expression for gradient is the same as this expression for gradient. Because they are the same, they can be made equal to each other, thus cutting out the middleman. There's only one variable left. The rest of this is just rearranging and solving for a. That's actually it for this particular example. I did take it a step further in case you did also need the tangent line. But this one pretty much just stopped at getting the a value. Notably, that wasn't the gradient. A was just the x value of the point. To get the actual gradient, you would just shove it back into either this or that, whichever one you prefer to sub into. Both of them are relevant. You get your m, and we already have the point, just replacing the a's once again with a equals a third. Now, these will always come out as linears with no plus c as well. Like very, very often you're subbing in, or your other point that the question is referring to is the origin. And well, because it's the origin, there would be no y-intercept, or at least the y-intercept will be 0. So you're going to have no plus c on your linear. How's that one? Making enough sense? Wait. Lastly, we're going to have a look at some angle-related stuff. So we've got a quadratic for f of x, and we want to find a tangent such that we get a 45-degree angle anti-clockwise from the x-axis. So they'll always specify whether it's clockwise or anti-clockwise. In the vast majority of cases, it'll be anti-clockwise. Yeah, we can definitely go over quotient rule for sure. So what I'll do is I guess I'll just finish this example here, then we'll move on to some quotient rule stuff for sure. Okay, so first up, basically, if it's not given as anti-clockwise, it's ideal that you do convert that back into an anti-clockwise expression, whether that means putting a negative on your thing or just whatever the equivalent is the other way around. So you'd have, I don't know, like say 180 would become negative 180, or 90 could become what's that, negative 270. Yeah, either way, basically doing the flip of that, because when you sub that into your tan inverse, that'll actually get you the correct gradient that way. But either way, it's pretty much always going to be anti-clockwise. This is only as a as a safeguard, essentially. From there, get your gradient using tan theta. That's going to get us, well, the gradient that we require. It's most of the time going to be a 45-degree angle as well, which makes it nice and easy. So as long as you've got your tan values memorized, then this should be fairly chill. Now that gets us gradient, perfectly, sure. But what we'll notice is that there's no actual x or y information for the point at which we are finding this gradient, this tangent at. So far we have gradient information, which means that the derivative should be pretty helpful for us here. So getting our derivative gets us an expression for gradient, and because we have the value for gradient, well, we just marry them up, make them equal to each other. That's going to get us the x-coordinate for which we have the gradient of 1. And of course, once you have an x-coordinate, you can get the y-coordinate by just shoving that back into the original function. Up until now, we're going to now have gradient, x, and y. So just shove them all into where they belong. That's pretty much it there. Fair enough on that one? Cool. Okay, let's have a look back at the quotient rule stuff. So was there anything in particular that was off about the quotient rule? Or do you want me to sort of...
Like, understand the formula, but then pretty much every chapter question that I'm doing, I'm getting wrong.
Getting them wrong, okay. I wonder if they are getting wrong or if they are just simplified differently, perhaps. Did you test them in the CAS and see if you get the same answer in the book?
No, I'm not getting the same in the CAS, and it's mainly that I then will look at the working out, like the work solutions, and have no idea what they're doing.
Sure. Okay. So the work solutions are looking a bit different to what you're used to seeing. Okay. Tell you what, I'll pull up. Do you have any examples that you wanted to specifically have a look at with quotient rule?
The first one that I really got stuck on, it was from 9K, question 3A.
9K 3A. Oh yeah, because of the root. I could imagine that being a bit strange. Let's have a look. I'll find my answer doc somewhere. Let's see here. That's 9K 3A. Okay, let's see if they're doing anything weirdly going on here. Oh, is it this sort of notation that's a bit weird? Or do you understand that?
Yeah, so that notation's weird, but then I find myself getting to a similar place beyond that step. But then where they go from there confuses me.
So perhaps here is where you're getting up to, or?
Yes, most of the time that's where I get up to.
You get onto this stage here, and then... Oh, actually, this does seem a bit strange. Where's the... Am I in the right chapter? Oh, this is product rule. Yeah, that's why. Are you using quotient rule stuff for this, or?
This one I tried. This one I used product rule.
Yeah. Okay. Cool. I was like, where's the fraction? Then I realized it's product rule. Yeah. Okay. Let's see. So what have they done here differently? I'm noticing a common factor here. So basically, the next line of working is going to be taking out a portion of this. Now, it does have different powers, yes, but because the bases are the same, they're doing some form of taking out a common factor. So let's see if we can explore that in a little bit more detail. I'm essentially going to pull up some working out here, or the written notes, and I'll copy down the last line, and I'll see where we can go from there. Okay. We had x plus 1 bracket, and that was the half squared plus 1 to the minus half. There was also a 2x. And then there was a plus. In fact, maybe this set of brackets here is a bit kind of redundant, because this is all multiplication anyway, so that might just be a cause of confusion perhaps. Okay, and then there was the plus x squared plus 1 to the power of a half. Okay, so before I do anything here specifically, what kinds of things would you do to start simplifying what you're looking at?
Just quickly, how did you get the 2x?
I've just copied down what they've written.
Because I had the same rule written down, just without the 2x.
Oh, okay, cool. Let's try and figure out where they got that from then. So we'll leave that there for now, and we'll just do product rule from the start. So this is 3a, we have our x plus 1, maybe I should define it first. So get our u and our v. U equals x plus 1, v is going to be root x squared plus 1. Okay, u dash, that's going to be real easy, just derivative of that. V dash is where things are going to get a little bit more complicated. What rule do we need to use for getting our V dash?
Chain rule?
That's it, chain rule. So how are we going to make that work?
X squared plus 1 to the power of a half.
Yep, so first thing would be maybe like rewriting it so it's a bit easier to see what's going on. Yep.
So then 1/2. Oh, yes, you would get the 2x from getting the, yes. No, I see it now.
Cool. Okay. So that might have been the main difference that would have maybe confused a bit of your working out, perhaps. From here, I guess it'll be a matter of, you've got this half and you've got this 2. Those are going to cancel down on them, leaving you with just a x over there. And then from here, it'd be taking the common factors out of these, is what they ended up doing, I believe, if we have a look back at the answers. Yeah, because you got the x plus 1 from there. That's still kind of in there. X squared plus 1. And that bit's being taken out. So was that the main thing that was the confusion there, or do you need to see the rest of it?
Yeah. Could we go through the rest of it, if that's okay?
The rest of it? Yeah, sure. Okay. So let me grab a copy of this down here so we can start working on with more space. Got x plus 1, we got x squared plus 1, power of minus half. There's also an x. And we got plus x squared plus 1, power of half. Cool. So from here, probably one of the things to do would be to expand out the x and the x plus 1. So it's going to give us x squared plus x. Then we have our x squared plus 1 minus half. And then plus again x squared plus 1, power of positive half. Cool. Now, from here, expanding things out further is just going to make it probably more complicated than anything else. So that's why they probably elected for a fully factorized approach instead. So basically noting that these have the same base, essentially we're going to take out as much out of that as we possibly can. And you can go through it in a couple of different ways. They've elected to remove any negative indexes, which is probably the preferred approach. Having negative indexes is typically harder than, or more complicated than having your positive indexes left over, which is why they've taken that out as a common factor. It does make it a bit harder to see how the factorization works though, so it's worth having a quick revision to be like, hey, if we have something like this, right, you're just taking out the same amount from both. So the biggest that we could take out of both would be the x squared, giving you a plus x like that. So we need to take out, in this case, if we're taking out negative a half, we need to take out negative a half from this, but also take out negative half from that. Removing a negative is essentially going to count as adding it, right? Double negative makes a positive. So how this will end up working is going to be x squared plus 1 power of negative a half. This is the coefficient of that, so that's going to maintain as what it was. And then this is the bit that you're taking as much out of. Negative a half plus a half. You end up with now an index of 1. So because it's index 1, you can basically ignore the power from here and just have plus x squared plus 1 again. And if we check exactly what's in the answer sheet, that's how that's going to be. You got the x squared plus x, and you got the x squared plus 1. And then obviously from there you got 2x squareds in there, so you just combine those together. Bit weird how their factorizing works with negative indexes, but is it fair enough now that I've gone through that?
Mostly. Why, if you're taking away negative half, why wouldn't you take it away from the other one as well?
So taking away negative a half looks like this, minus negative half.
No, I mean for the first one.
Yeah, okay. So basically when it's taken away, it's taken out of the factor. So it's kind of like this example here, right, where we had removed the x squared from the thing. Because the thing that you're chosen is identical, the whole thing comes out with it. So, this x squared is fully removed because you've taken it out. You've taken out exactly the factor. Whereas because this isn't exactly, you're going to have some remainder left over.
Okay.
Sweet. Sorry, I was outside. What are we doing today? We're quickly reviewing some of the quotient rule stuff. And the agenda for today is namely going to be on like the tangent to normals, as well as the application of that further, which goes into Newton's method. But before going into any further regarding that, was there anything else specific from this chapter you wanted to have a look at?
That's good, thank you.
That was it? Cool, okay. But yeah, so I imagine it's going to be stuff like that where the diff-related notation's a bit strange, and you can see because there are roots involved in all of these, dealing with like power of negative halves and such can be a bit strange. So it's nice to do like little mini examples of stuff that's easier and then try to apply that backwards. And even further would be to, once you do give it a shot, just expand it back through and see if you get what you get. Actually, even better, one other thing you could do is, because these are kind of complicated bases, you can even do little substitutions in there. It makes the terms look a little bit easier and hopefully makes it a bit nicer to do your factorizing. Those are just some parting wisdoms there. But okay, so just to quickly recap for the tangent and normal stuff, essentially we are trying to find linears that intersect a function that also share the gradient that the function does at that point. So to catch Nihal up, basically there's a few main ways you can go about that. Pretty much in every case, you're going to have f of x, so you can always get f dash to help you find gradient-related information. And depending on the complexity of the question, you might also need some supplementary ways of also finding gradient. Namely, doing your rise of a run, because it is linear, you can use rise of a run, so long as you know 2 points. And if you know angle-related stuff, you could use tan theta to get gradient as well. We've got a bunch of examples here. We'll go through some together anyway, so hopefully that'll be enough to catch up. The last thing in this document is the normal line. Pretty much identical to tangent line, with the exception that instead of you finding the exact gradient that is shared at that point, you're now finding where it would intersect at a 90-degree angle. And all that means, as far as what we do, is once we find the gradient like we normally do, just do -1 divided by that gradient. That's it. All the other steps remain the same. So if we have a look at a quick example, finding the normal to a quadratic at x equals 2, we're going to follow the exact same procedure of getting the full point. So instead of just having the x, we now will also get the y by subbing that into our f of x. Finding the gradient using whatever method is required. In this case, we only have f of x, so we're going to use f dash to get that gradient. F dash, shove in the x value to get the gradient. Because it's normal, all we're going to do is take that gradient and flip it over -1. That's it. We now have gradient, we now have point. Chuck those into your either gradient point formula, like I've written here, or you could do the whole y equals mx plus c approach via like a two-step substitution there. Just to catch you up as well, I have tried both methods, and the lines are working out are identical, so it's purely and simply as much of a point of preference there. No one method is going to be slightly faster than the other. You'll also find that the normal lines are a bit weirder. They pretty much will always come out as fractions. So that's to be expected. The CAS also can do these for you directly, so this is going to be really helpful. You pretty much will always do this in every tech active exam, finding some form of tangent line. It's really, really strong because not only does it work with like known values of x, but also variables as well. So if you wanted to find fully generic tangent lines for any given point, you can just do like, instead of giving the actual x value here, you could just do like a or b or whatever, and it'll come out where basically every a or b that you've used, just plug in for whatever x value you want to take your tangent at, and you'll get the tangent line at that spot. It's pretty cool and pretty useful. Similar normal line also exists for them as well. Cool. Let's crack on with an example. So let's see, we got a good one. Some of these are fairly basic, where you're just finding the tangent or normal at a particular point. I'm going to try and find one that's a bit more involved. Yeah, let's see if we can jump straight to 5. If that's a bit complicated, we'll go back to the easier ones. Okay, so what's 5 all about? 5 is about finding the coordinates on a quadratic for which we have a gradient of 3, and thus find the value of c such that it makes this linear tangent to the quadratic. So it's tangent adjacent, obviously, but rather than actually finding the tangent line equation, we're trying to figure out what the y-intercept of the tangent would have been. I will drop the, actually what do I need to give you specifically? Probably just this. Oh no, they're not in blue. Usually my steps are in blue, but now they're in black. Oh well, another thing to fix. Cool. Alright, I'll get that as a screenshot for everyone. Mainly you're going to be doing this related stuff here. Alrighty, any takers? Who wants to try and start us off? I'll give you time to revise the notes, of course. Okay, maybe we need to do one together then. Let's take it a step back then and just work on one of the fundamentals here. So we'll just do like a 1a. So find the equation to x squared minus 1 at the point 2, 3. So let's have a look there. Y equals x squared minus 1 at the point 2, 3. So to find a tangent line, we need to know the gradient of the linear as well as the a point that exists on it. Now the good news is we already have that point, right? We're trying to find the tangent at that point, so it should also exist on the linear. So half the job is done now. All we need to do is now find the gradient at this point, and then we'll have all the information we need for our linear. Based on the information that we have, how could we potentially be finding that gradient? Uh-oh. That's fine. I'll run through it. So basically differentiation. Differentiation, when you find the derivative of a thing, gives you gradient information of that thing. So if we know what the original curve is, we can always find the derivative of that, thus getting gradient-related information of it. So we do our derivative dy dx, giving us 2x in this case. Because we want to find the gradient at this point, what we're now going to do is shove in the x-coordinate of that point into our derivative function, thus getting the gradient at that particular point. So it's going to get us 2 by 2 for 4. So m gradient is going to be 4, p our point, gradient and point. We can now do our linear, that getting the tangent line. So let's use y equals mx plus c, why not? So starting with y equals mx plus c, we essentially will now have gradient, so y equals 4x plus c, and our x and y are going to be 2 and 3 respectively. 3, 4, 2 plus c, 8 plus c, and 3 take 8, 5 minus 5. So finally, y equals 4x minus 5. And that gets us our tangent line. Those are the fundamentals there. We only build on it from there. Any questions about how that's came about? If so, let me know. Otherwise, we'll move on to trying the question 5.1 now. So a little bit different. We're told the function, still the same. Now we're actually told the gradient information ahead of time. So we're told gradient information. We're not told anything related to the point. Given that being the case, what kinds of things might be relevant for us to start finding? Oh no, we're all in holiday mode. Cool. Because we have gradient related information, derivative is going to be helpful here. So because derivative gets us gradient, pretty much whenever you're doing anything that says tangent, gradient, anything like that, if you can get the derivative, it's usually going to be pretty helpful to get the derivative. So let's do exactly that. dy dx is once again going to be 2x because the constant doesn't matter. Because gradient is 3, we now have 3 equals 2x. X is now going to be 3 on 2. So that gets us the x value for which you would have to take your tangent at to get a gradient of 3. Now, from there, our goal was to find the value of c for which that linear would become tangent. That's not actually a different question, realistically, as far as the steps you follow, because that linear that they've given you is fundamentally a tangent line, just an incomplete one. So whether they've given you some pre-completed stuff or not is kind of irrelevant. We're still following the exact same steps here. So we've got an x-coordinate. All that's left is to get the corresponding y-coordinate, which of course means shove that in there. That's pretty much it. So let's do that. Y equals 3 on 2 all squared minus 5. Y equals 9 on 4 minus 5. Y equals, so 9 minus 5 was 20 on 4. Y equals, what are we looking at there, minus 11 on 4. We get our y coordinate, we get our x coordinate, and we have our gradient. So this time I'll use the gradient point formula. Again, they're the same thing. Y take y1 equals mx take x1. Our y1 is going to be minus 11 on 4. So remember, we have a double negative here. So it's going to go into positive 11 on 4. Our gradient was 3. 3 right there. And our x value was 3 on 2, which we solved. So x minus 3 on 2. And from here, yeah, we're just going to simplify. Y plus 11 on 4 equals 3x minus 9 on 2. Y equals 3x minus 9 on 2 minus 11 on 4. Maybe we'll quickly change that 9 on 2 into an 18 on 4. And finally, y equals 3x, what's that going to be, 29. 29 on 4. And to actually finish up the question here, we weren't told to find the tangent, we were told to find the value of c. So what we're going to do is say, finally, c equals negative 29 on 4. C equals negative 29 on 4. And give it a nice underline or circle, or however you want to highlight your answer. Fair enough? Any questions at all? Yeah, that's pretty much all tangent's going to be. It's going to be following that procedure for the vast majority of cases. In other more complicated cases, you're going to have to do those like equating the two things. Do you want to see or try any examples like that live together, or do you want to move on to the next topic?
Can we do one more example?
One more example, sure. Of similar difficulty to this, or do you want to do like the other, like newer examples?
Maybe similar difficulty.
Similar, sure. Cool. That was question 5. Let's see. We got one that's similar. We've got one that's quite so similar to that. Let's see. It's going to be find tangent at that. Yeah, okay. Maybe 11C will be similar enough. So find the equation of the tangent to our function, which has a coefficient involved in there, at a point that also has a coefficient involved. So we have point information, we have f of x information. We just don't have any gradient related information. That's the last thing left to find here. So how do we normally, well, what's one way we could get our gradient related information?
Find the derivative of the log.
Yeah, absolutely, derivative of log. So how do we get our derivative?
It would be k over k of x.
Yeah, it will end up being k over kx, absolutely. K over kx, which of course, we're now going to cancel that down. Which, fun fact, is why this is the only thing in the table of derivatives that doesn't have a coefficient there, simply because that coefficient always cancels itself down. But yeah, nice find. Okay, we got our f dash. What are we going to do with it?
Substitute in the x value, which would end up just being k.
Yeah, precisely. So 1 over k, the 1 overs essentially cancel themselves out. So f dash 1 over k, which is our gradient, is therefore k. We have gradient, we have point. Our goal is to find the tangent. If we need anything else, what do we need? Or could we just start going for it?
Are you able to just put it into the equation, or is it different because it wouldn't be a linear equation?
So the equation that we're putting into is never going to be f of x. We only use that to get x and y information for the point. The equation we're putting things into is either a generic y equals mx plus c, or that gradient point formula method that I showed you up here. So you're always putting it into a linear at the end of the day. You just need the gradient of the linear and the point that the linear will go through. So that's a nice thing about tangent lines. It doesn't really matter what this f of x is. If it's complicated enough, it might even be tech active, in which case you don't have to think about how you get your diff either. You just cas it out and it's fine. So yeah, the complexity of this is irrelevant. It always just goes down to linear at this point. So generic y equals mx plus c. Our gradient was k, so this is now going to be kx plus c. And our point is 1 over k comma 0. So 0, k, 1 over k, whoops. K, 1 over k plus c. 0 equals, well, k over k, which is going to be 1. And therefore c equals negative 1. We have our c value. We already did our m value. All that's left is putting it all together. Y equals kx minus 1. And that's fully valid because we only had a k for our point there. Any questions about that? Cool. We did have a couple of other examples that were a bit more involved. Do you want to look at those as well?
Yes, please.
Sure. Okay. So we did this. Actually, no, we did a bit of a tougher one slightly. So let's do. Well, these are all the same thing. Let's go with this one then. We just kind of did a log already. So we're given point information, and again, it's generic. And again, hang on, is this going to be different? Let me have a quick look. Yes, this will be different. Cool. Okay, so we have our function information, we have our point information. In fact, we have 2 points worth of information here. So I'll start writing all that down. In the meantime, just sort of keep in the back of your mind, ultimately, we're trying to find tangent lines or things that are adjacent to tangent lines, which pretty much always boil down to we need gradient and we need a point. So whatever's missing is what we should start working towards. So I'll start writing things down. In the meantime, have a think about how we might progress from here. Our goal is to find the value of A. Effectively, that means we need to somehow create equations that have A's in them. So that's one sort of guiding piece of advice, right? Looking at the thing, the deliverable, and then trying to figure out how you're going to get equations that have the variable in it. The other thing is sort of the context clues around it. So we'll forget for a moment that this is in the tangent lines chapter specifically. It's more so the fact that it says the tangent passes through the origin. That keyword tangent should start inspiring ideas of gradients, of derivatives, of rise over run, maybe angle for tan theta stuff. Even if it's not immediately obvious what you would do with that information, pretty much as soon as you see the word tangent, start with f dash, rise over run, tan theta, whatever you can use with the information that you have. So we have a couple of options how we could progress from here then. Where might we start? Okay. So if we go down our list of possibilities, let's just pull that up. So finding gradients for tangent line. So one thing you can do is just do f dash, right? If f dash is available, we can try that. So let's see what happens. We do have our function, so we can get our f dash here, or in this case, our dy on dx. dy on dx is now going to be 2x plus 2. So right off the bat, we've got gradient related information there, which is nice. Now we're trying to find it specifically at a point. So rather than just having the fully generic... What? Uh-oh. I just crashed. What the hell? My internet crashed. Oh no. Okay, my apologies. Apparently my internet crashed. How long has it been since my internet crashed?
Not that long. I thought there was something wrong with my headphones. You were just writing out the derivative when it cut out.
Yeah, because I looked up to my screen as I was mid-talking. I was like, why didn't the derivative update? I was like, why is it not there? And then just the entire Zoom just crashed. I was like, oh shit. Okay. Cool. Okay, so I was writing out the derivative. What I was saying from there, now that we have our derivative, have I got the screen share back up? Okay, everything else is looking good. Cool. Now that we have our derivative, it's not so much just finding the derivative, but more so the whole point was to get gradient information. More specifically, gradient at the point of which is going to be generic with a's involved in there. So we had the point a comma a squared plus 2a. So rather than just having derivative there, we actually want our m, our gradient, and nice and simple, we're just going to put in the x value for which we had that point. All right, we had this point up here, x value is going in there. What we'll start realizing is that we just created an equation that now has an a in it, which is really nice to have. Cool so far? Have I caught up properly?
Yeah, that makes sense.
Okay, awesome. Now, the equation that we have is nice, but it's got two variables involved. It's got both the a and the m. If we're trying to solve for a, at least, we're going to need another way to get rid of this m. Any thoughts on how we could either get rid of this m or somehow replace it?
Would you not be able to just input that value into the equation?
How do you mean? So as in the linear equation?
Yeah.
Yeah, so if we're trying to find tangent line, yeah, that would be our gradient purely in terms of a. Absolutely. So you'd have y equals m, where m is 2a plus 2, x plus c. This question is a little bit different because we are ultimately trying to get to the value of a specifically. But yeah, if all we had to do was find tangent line, then yeah, you could start doing things like this, and then you would sub in your point involved as well, and you would get it fully generic in terms of a. So for instance, you'd have the a squared plus 2a as the y value. You'd have the 2a plus 2, x is now, oh, it's just a. And yeah, plus c. And then fully simplifying from here, a squared plus 2a equals 2a squared plus 2a. 2a is going to end up cancelling off of each other, and one copy of the a squared is going to disappear. A squared, negative a squared is c. So finally, we come back up to this bit. You would then end up with negative a squared there for your c value. And that's perfectly fine for a tangent line. That is the generic tangent line for this quadratic. Whatever a value you use, whatever spot you want to find the tangent at, you just plug that in and you get the tangent line for it, which is pretty neat. So that would be what we would do to get the full tangent line. Our goal is still to find the value of a. There's some more information that we had in the question that can help us get there. Namely, we had the origin as well. We know that our tangent line has to pass through the origin. With that in mind, how can we start maybe working towards solving for a? There's actually a couple of methods I can think of that'll get us there. Reminder that this thing here is the tangent line. This is the thing that has to go through the origin.
I'm not sure.
Not sure. That's okay. So this point P2 here being 0, 0, the origin, is a point that's supposed to exist on our tangent line. So having gone through the procedure of getting the generic tangent line, we can just actually sub in that point, thus replacing an x and a y. It's a point that should exist on the line, so it should be able to be subbed in. So we would just go from there, right? 0 is equal to 2a plus 2x, where x is also 0, plus our c, so minus a squared. That's going to all cancel down, leaving you with 0 equals negative a squared, or just 0 equals a. Which seems a little bit suspicious. 0 being a. Definitely works out for the plus c, since you want it to go through the origin. So this is just y equals 0, the horizontal line. Does that make sense for this graph? Maybe. I'll do it the other way as well, just to validate. But that is definitely one way of going about it, unless I've done some weird algebra there. Because it exists on the tangent line, you should be able to sub in that known point and therefore get there. The other approach, if you don't want to go through the whole solving the tangent line, would be understanding that this is a rise of a run, right? That's a point that exists on the linear. That's also a point that exists on the linear. So you do your rise of a squared plus 2a over the run of a. That is also an expression for gradient. So if that is also, yeah, so having 0 there seems really suspicious. Oh, wait, no, it wouldn't have been 0. Yeah, because a is 0, but then you're adding 2 to it. Yeah, okay, so that should be fine. Anyway, so we have our expression for gradient here. We have our expression for gradient here. We can now make those two things the same. Let's do that down here. So 2a plus 2, that's that expression for gradient, is equal to that expression for gradient, a squared plus 2a over a. A squared plus 2a over a. One thing I also neglected to see was that a is a common factor of all these things. So cancels, cancels, cancels. You're left with 2a plus 2 is equal to a plus 2. cancels, cancels. And once again, another way of getting to a equals 0. So you can see that whichever way you go about it, whether you create your full tangent line or whether you do the rise of a run thing, both of them will get you to the a equals 0, thus giving you the final tangent line, if you needed it, of 2x. Because the 2a goes to 0 plus the 2 at the end. That's a couple of ways of doing it. Anything in there that needs more clarification?
That makes sense.
Makes sense? Cool. It's one of those things where you just sort of need a bit of practice to do them. And the good news is you do have a lot of practice here to be done. So question 14 all the way to 17 are all the exact same question, just with different functions that are involved. 13's a little bit different. You're now finding distances rather than tangent lines. You're still doing all the related stuff, but I'm assuming when you do question 13, you'll basically have 2 points. You'll have the origin and whatever the point A is, which is going to come from here, I guess. You find those 2 points, then you would just do your distance formula using similar techniques to this. I'm kind of glossing over that one because we're about to hit time here, and I think it'd be worth quickly introducing the last topic, which is just an extension of tangent lines, essentially, which is the Newton's method stuff. So Newton's method is, as I said, an application of tangent lines. What you're essentially doing is finding a bunch of tangent lines that get closer and closer and closer to where you want them to intersect. So to give you a bit of background, not all equations can be solved analytically using just raw algebra and getting a nice, easy, closed form solution. Sometimes you just get really, really challenging to find answers. Like cubics will typically do this. Not all cubics can be factorized, and you can find even surds, right? It can be still complicated to find like a square root 3. Sometimes you'll just have to make do with the decimal approximations of them. Newton's method is one such approach to help with these equations that can't be solved with algebra. The idea is that as long as you know roughly where your solution should be, whether you plot it on a graph and then look in the ballpark or otherwise, as long as you know roughly where that is, if you take a tangent line on the original function, where that tangent line intersects the x-axis is very likely to be closer to the x-coordinate of that function that you're trying to solve. So this one is solvable with algebra. We don't need it, but it's just there for demonstration. So the red line is going to be that quadratic, right? And our goal is to figure out where does it cut the x-axis. And it cuts it around there, somewhere between x equals 1 and x equals 4. So the idea is that they said, okay, cool, let's just test x equals 4. That's going to be that blue line tangent. What we see is that where that tangent now intersects the x-axis is much closer to where we want it to be, right? It was at x equals 4 where we took our tangent. Now it's a lot closer. So then we say, what if I now take my tangent here at this new spot? That's going to be this yellow line. And sure enough, we see that intersects just a little bit closer. In fact, the change is quite dramatic. So going from 4 to like almost 2-ish there, a little bit over 2, to now pretty much on the ball, right? It's pretty close. And the idea is just keep doing that over and over again until you're satisfied with how close you got. If you take a tangent here, you would probably intersect somewhere like that. Take a tangent there, you can see how you would basically get closer and closer and closer to that actual value. Where you stop purely depends on the question. It could say be accurate to a number of decimal places, in which case you just stop as soon as you hit that number of decimal places. Like for instance, let's say we're trying to get our thing to 2 decimal places. That's a pretty common one. Your first iteration is 4, next is 2.25. As soon as you hit that 4th iteration, we can see that those leading decimal places are no longer changing. So this is where you end up stopping, and you just use this number as your final answer for the x-coordinate estimate. And you can see it converges pretty damn quickly. Like within 3 iterations, you're already accurate to 1 decimal place. Within the 4th, you're now accurate to 4 decimal places. Within the 5th, It just runs off the screen. Who knows how accurate it is? But it's, it gets accurate very, very quickly. If it says do a number of iterations, then that's even easier. You literally just do the number of iterations and you're fine. That's all Newton's method is. That's only why I sort of chucked it in at the end, more or less, as a quick little application of what you do. So you can see here, do it to X number of decimal places. And some of them are trying to get the actual equation itself. The equation, without going into too much detail since we're going to run over, is essentially a rearranged version of the y equals mx plus c. So you've got your y, your m, and the x, or the gradient point formula version, and you're essentially just rearranging that and making it generic to look like this. We can go into more detail if you guys are focusing more on it later on. In fact, I also have videos and other past lectures if you want to go into more detail on this, but it is a pretty minor thing where fundamentally all you're doing is plugging this equation into your CAS and then just hitting enter 3 or 4 times until you get what you need. The other thing to watch out for will be some of the ending conditions. Have you got time for like a couple of minutes to quickly run over this, or you got somewhere to be?
Yeah, not a problem.
Yeah, sweet. So it doesn't necessarily always work. There are some fail states for Newton's method, the first of which is referred to as the oscillating sequence. This is likely to happen when you have, I guess it's likely to happen when you have like these odd functions where they have that sort of diagonal sort of symmetry going on, where basically if you have a tangent line taken at a particular point, it'll intersect somewhere. If you then take the tangent line at that point, it'll intersect at the exact same spot that you took the original tangent line at. So basically this will keep going on forever and ever and ever, never actually reaching the middle. Odd functions will definitely do this, simply because of how they work, where they have the y value here is the same as the negative of the y value down here, which is why things will always kind of do that. The other issue is what happens if you chose a stationary point. Right? If you try to take a tangent at a stationary point, it's going to be perfectly horizontal. It won't ever actually touch the x-axis. That is referred to as the terminating sequence, because there is no other point for you to try and take your next tangent at. These are actually worth getting understanding, because there was an exam question in an extended response. I think it was like a 1 marker, maybe a 2 marker, that just said, hey, why is it bad to take our tangent line at this spot? In that particular case, it was because it was a stationary point. It was a terminating issue. That's about it. Anything to clarify about any of that? Makes sense? Sweet. Cool. All right. We also had the Friday as well to review things in more detail. So if you wanted to do more of this sort of stuff, we could have a look at that on Friday as well. Otherwise, yeah, there's also literally any topic we could have a look at on Friday, even if it's not in this curriculum here. Cool. All right. I'll let you enjoy the rest of your day. Thanks so much.
Thank you.